Okay, unit 8 of 10. We're going to talk about the accumulation function. This right here is the accumulation function. It is an integral with a variable in it. Okay? It's read the integral from 2 to x of f of t dt. But you can think about it as the accumulated area starting at 2 and going to some unknown of the function f. Now, a lot of people get really scared because they like f of t. What is f of t? Well, the t is just necessary so that these variables do not agree with each other. If they agreed with each other, all of a sudden, we would not be talking about the accumulated area under f. We'd be talking about, the accumulated area under these function values. So it's something not to worry about. If you have f of t, you can just exchange an x with a t. So this would be the accumulated area from 2 to x under f. Just think about it as f, okay? So that's what the accumulation function is. It is this integral from some value typically in the bottom. This is a, this is a number, to a variable x of some function. We need some different variable than this x so that they do not agree with each other of f of t. So of f dt. It is read the accumulated area from a to x under f. Okay, we're going to be working with this type of function today, this accumulation function. And first couple questions are kind of basic. I'm telling you that g, so some other function, is equal to this accumulation function of f. And I'm asking you to find g of 4, g of 7, g of 2, and g of 0. Now, for these first couple, it's very important to understand that 4 is where x was, right? So you will be replacing x with 4. So this question, what is g of 4, is the integral from 2 to 4 under f. And this is why we have t's here, because if I had x's here, I'd have to plug in 4 in for x. But I don't. Since I have t's, I just plug it in to the integral, nowhere else. Okay, so now this is an area problem. What is the area from 2 to 4? This is 4. So this is 4. Okay, you guys do g of 7, g of 2, g of 0. Just for practice, plugging in this value as an x and making sure we can find the correct areas. I'll go ahead and write down what these areas are for you so that you don't have to recreate the picture. Okay, just replace x with your value in your integral. Check your answers with a neighbor, please. G of 7, integral from 2 to 7 would just be 3. G of 2, we know it's the integral from 2 to 2. We know that's just 0. G of 0, this is the one tricky one. It's important that we're understanding that things are from right to left. When they're from right to left, they're the opposite of left to right. So this would be negative 3. Okay? Piece of cake. Well, I could also ask you the same type of question, but with a function inside. Instead of giving you a picture, I can ask you to use the fundamental theorem of calculus to evaluate this accumulation function at pi over 3. It's really the only difference between this and a problem that you did last unit was the fact that it's just, this is an x. All you have to do is take this pi over 3, plug it in for x, evaluate it using the fundamental theorem of calculus. Okay, but that's good practice. Remember to take the antiderivative of b minus the antiderivative of a. Go ahead and do that, and let's get our answers. This is also good trig practice. Do we remember how to get the sine of pi over 6 and the sine of pi over 3? Are we going to flip-flop the values or get them correct? Antiderivative of cosine is positive sine. Now, the antiderivative of cosine t would be sine t. Notice I'm not using x's for this antiderivative. It's important to kind of keep it separate. That way, we're just using correct notation and we don't make any mistakes potentially because of our notation. The antiderivative of b would be sine of pi over 3. The antiderivative of a would be sine of pi over 6. How do I do it? In my brain, I create that triangle at pi over 3 with the 60-degree reference angle. I remember my 30, 60, 90 triangle. I know that sine is the y, or the vertical side, over the hypotenuse. This would be the longer side. And then, so that's root 3 over 2. And then if I do pi over 6, I think about a 30-degree reference angle, making a short 30, 60, 90 triangle, sine being the y, or the shorter side in this case would be 1/2. So I get root 3 over 2 minus 1/2. You can simplify that to be root 3 minus 1 over 2 if you wish. Good. All right. Well, let's look at what the derivative of this accumulation function is. And this is what we will end up being our second fundamental theorem of calculus. Okay, I'm going to use this from the previous example as kind of our example. And hopefully after doing this example, we'd be able to come up with like a general derivative for this. Okay, so I'm going to attempt to take the derivative of this accumulation function. Now, I do not know how to take a derivative of a definite integral right now. I kind of know that if I took the derivative of an antiderivative, what would I get? Yeah, whatever is in here, if I take the derivative of the antiderivative, kind of get what I started with, right? Does that make sense? Well, we're going to see how that kind of works out for a definite integral, because we know we can find a definite integral by the fundamental theorem of calculus by taking the antiderivative. So I'm going to work inside out. I'm going to leave this derivative symbol. I'm just going to say, let's take the derivative at the end. Let's go ahead and define the cosine of t dt, integral from pi over 6 to x. I start by taking the antiderivative, which is sine of t. I'd be finding the change of that between pi over 6 and x. Notice I have t here for sine because I have x here. Well, I'm going to plug in x and pi over 6 because I don't know how to take the derivative of this with this line. I'm going to keep the derivative symbol on the outside. I'm going to say, okay, I'd be taking the derivative of sine x, which is this antiderivative at x, minus the sine of pi over 6. Okay, well now I do not have integrals, I do not have lines, I can take the derivative of this. What is the derivative of sine x? Cos x. And what is the derivative of sine of pi over 6, Mr. Shesker? Wrong. Sorry, I picked on you there. Everybody gets that wrong. Anybody else, think about it for a second, can tell me the derivative of sine of pi over 6. 0 is correct. Why is it 0? Sine of pi over 6 is a number. It is a value. Derivative of value is 0. Okay, so I started with something that looked complex, taking the derivative of this. Okay, and I ended up with cosine of x. What is that? That's just the function that's inside my integral with x's instead of t's, right? How did we get there? Well, think about it. We have to take the antiderivative to find the area, but then we're just going to be taking the derivative of that antiderivative to get where we started. So what we'd find out is that for any function, the derivative of this accumulation function is just the function with the x plugged in. You just got to take that x and plug it in for t. You take the antiderivative using the fundamental theorem of calculus, and then if you take the derivative of that, you're back where you started. However, this is an a. For this one, I had pi over 6. What if I change this pi over 6 to a pi over 2? Would that change my answer of cosine of x? Why not? Still a number. This is still a number. The derivative is still going to be 0. What if it was 0? Still would be a number. It would still be 0. It's very important that you see that this is a. A can be any number, and it's still going to kind of disappear on you. Doesn't matter what a is. It could be any number. The derivative is still just going to be the original function with x's. Now, here's a little challenge, a little sidebar. What if I flip-flop things and I went from x to a? Mr. Urban, why do you say it's going to be negative? Right? Yes. Backwards. Exactly. If I flip-flop things, all of a sudden, my a value would be here. This would now be a number. The derivative would be 0. X would be here, but this is going to be after this minus sign. So all of a sudden, I'd have 0 minus cos x. So the opposite. It's almost like we take that and we don't make the x negative, but we'll take the opposite of whatever that f of x is. Okay? Now, you will have some problems that you will have on your test, on the AP exam, that are going to be some of the easiest problems out there if you are familiar with the notation and with this fact that we just discovered. Something like this. What is the derivative of the integral from negative 12 to x of root t squared plus 1? Go ahead and write that down, and then I'm going to just say something before you do it. So many of you will be able to do it. Now, some of you will feel like, oh, I need to take the antiderivative and then plug in the values and then take the derivative. No, in the future, you will just skip these steps and you will go straight to the whole inside function with x's. You will go straight to this. Do not try to take the antiderivative of root t squared plus 1. You're not going to be able to. It's one of those things where it's just, you can't do it. Instead, just use this kind of shortcut. Okay? And write your answer. Go. What'd you get, Mr. Van Buren?
Root x squared plus 1.
Yeah, it's just root x squared plus 1. You can think about doing the steps in your head. Don't do them. You can think, oh, I'm taking the antiderivative. I'm plugging in x. I'm plugging in negative 12. Then I'd be taking the derivative of that antiderivative, giving me the original with x's. And then I'd be taking the derivative of the antiderivative with negative 12 plugged in. The antiderivative with negative 12 plugged in will be a number. Take the derivative of that, that'll be 0. Okay? So, piece of cake, you will see problems like that. And you should all get it, because you're just taking this x and plugging it in. The important thing is because you're taking the derivative of it. It's not the accumulation function, you just don't plug in x. It's when you're taking the derivative of the accumulation function. Now, let's look at something a little bit more complex. What if we have a function instead of just x? What if we have some h of x in my integral? Let's try to take the derivative of that. So an example that I can do is the derivative of integral from 3 to x to the 5th plus 2. I'll go x to the 5th plus 2x of sine t dt. Well, I'm going to do the one on the bottom, and hopefully that'll give me the simplified way to do any of these. Now, using the one that we just did up above, what do we think the derivative of this accumulation function will be? Right, you think you just take h and you plug it into t, and you think that this is just, f with h of x plugged in. Well, let's see if that's going to be right. I'm going to do this step by step because I can take the antiderivative of sine. I can then take the derivative, so I can go step by step through this and see if that's going to be correct. So, again, I'm not going to take the derivative just yet. I'm going to take the antiderivative of sine, which is negative cosine. T, I'll be plugging in 3 and x to the 5th plus 2x. Okay, so I'll be taking the derivative of negative cosine of x to the 5th plus 2x minus negative cosine of 3. Now, negative cosine of 3, what's the derivative of that? 0, right? Again, we're plugging in a value into that antiderivative. It is a number. Derivative of a number is 0. So I have to just take the derivative of this piece, and I get the derivative of negative cosine is positive sine of x to the 5th plus 2x. Am I done? No. What do I have to do, Mr. Lenz? Chain rule, multiply by the derivative of that inside, which is 5x to the 4th plus 2. Okay, and again, it'd be plus 0. So I wanted to take the derivative of this, and I got this. Is this f of h of x? No. What is it, though? Excellent. Excellent, you guys. We have to multiply by the derivative of that function. So there's actually like an extra step if we have something other than x. Now, if we have x, we could be thinking of doing it this way. F of h of x times 1, because the derivative of x is 1. But it's unnecessary, right? Because you're just multiplying by 1. But if we have something else, we have to multiply by the derivative of that function. Now, we will have problems on the AP test, and on your test, that will be like this. And again, this is the shortcut. This is what we need to do. Do not try to do every step along the way. It will be unnecessary. But you will have to remember this fact here. The previous problem that we did the example of, 90% of AP students will get that right. This problem right here, all of a sudden the percent goes from 90% to 30% of students get it right. Why? Because everybody forgets to multiply by the derivative of the function that they're plugging in. Everybody just takes this x cubed and just goes in here and goes in here, and they see that as one of their answer choices and they select it. But if there's something other than x, there is an extra step which everybody forgets, and you guys won't be part of the 70% who gets this wrong. You'll be part of the 30% that gets it right. You will multiply by the derivative of that x cubed. It's just one of these things on the AP test that we have to remember. And it could be either a slam dunk problem or a problem that you'd never get right if you don't remember it. Okay, now you could go through and do it step by step, but it's going to be a lot quicker. And on the AP test, time is a factor, especially on the multiple choice no calculator. And you get that answer, boom, you circle it, boom, you spend more time on a problem that's more difficult. Okay. This one you can't do step by step. This one you have to do using kind of our derivative of the accumulation function knowledge. So go ahead and write down that answer. Make sure your answer is the same as your neighbor's answer. Seems so simple, and it is, but it's something that is easily forgotten. What is that? Like a box that's lockable? Combination box? No. Weird. Is it just something that keep you occupied kind of thing? Like a... Cool. Okay, it's just plug in sine, multiply by the derivative of sine. Piece of cake. Questions? All right. Well, this brings us to, one more, where I have a function on the top and a function on the bottom. I'm just going to make this x cubed and x squared. Could you tackle something like this? And you'll see something like this on your homework. I would not do it step by step. You can use the shortcut. Here's the key. What's the difference if I have a value on the top and a function on the bottom? It'd be negative, right? Well, for this, it's just going to be your top plugged in times your derivative. And then the bottom will also be plugged in, but you're going to subtract it. Okay? So you will see something like this on your homework, maybe on a quiz. So it's not that hard if you just put 2 and 2 together. And I would just leave it like that. Maybe simplify if you really, really want to. All right. Now, this will bring us to the second fundamental theorem of calculus. we typically will say this accumulation function is some other function g of x. Okay? However, kind of going through the process that we went through before, we will find that g has a relationship to this function f inside of my integral. Okay? And it's easy to see that relationship if we take the derivative and then take the antiderivative of this situation. Okay? So I'm going to start by taking the derivative of both sides. What is the derivative of g? What can I write that as? Just g prime. And from previous examples, we know that the derivative of this is just f with the x plugged in. So it turns out the derivative of g is equal to f. Well, watch what I can do here if I take the antiderivative of both sides of this. What would we say is the antiderivative of g prime? G. What is the notation we typically use for the antiderivative of regular f? Big F. Oh my goodness. This can change this statement to this. Turns out G, the accumulated area under F, that function is actually the same as the antiderivative function of F. They're the same, which means this accumulated area under F is the same as the antiderivative function of X. Okay? All three of these are the same. This is the second fundamental theorem of calculus. It equates definite integrals to antiderivatives. It's kind of like what we already did with the fundamental theorem of calculus, just looking at it a different way. Okay? So, here's a question that we can kind of use this fact to exploit and get the answer of. I don't know the antiderivative to e to the 3x, x to the 4th, but I can write an expression for the antiderivative, right? Because I know the antiderivative of f is big F. I know that we can write big F as just the accumulated area from some value, it doesn't matter what your value is, of your function just using t's instead of x's. And maybe if I had my calculator, I could find antiderivative values that I'm looking for. Typically, we'll need one extra point to kind of know where we start. Okay, good to know. Now, what we will be doing, though, typically with this second fundamental theorem of calculus, is doing function analysis. So, like problems like this. I'm giving you that G is equal to the accumulated area under F. I'm going to ask you what the derivative of G is. I'm going to ask you when G has maxes and mins. I'll ask you when G has inflection points. All that good stuff from Unit 4. However, it's going to be a Unit 4 with the accumulation function. Okay, we'll get to that. Here's the key. This table that I will create can be created for all of these questions when you're asked to do function analysis of G or of big F. We know the derivative of G is G prime. That's just going to be equal to F, which means the second derivative of G will equal the first derivative of f. We will be given information about f, but we can use that information to find information about g. Given information about f, use this to find info for g, which is also the same as big F. All right. So here are your first kind of types of problems that you will see that kind of goes beyond just area. I'm giving you that g is equal to the integral from 4 to x of f of t dt. We have this graph that we're used to seeing. I'm going to ask you for g of 3, g prime of 3, and g double prime of 3. However, the information I give you is the information for f. Go. Okay, discuss with neighbors, help your neighbors out. Some of you have this under control, and I know some of you are like, I'm not sure. I don't know what to do. I'm lost. Go, discuss. First one everybody should do. We did a problem. We did those problems at the beginning. But the second one and third one, that's when we got we're going a little bit different. It is a lot simpler than you think, because all you need is this. And this. Right, it's a piece of cake. It's nothing too tough. G of 3, area from 4 to 3. Well, we should get that. Okay, that's going to be -2 because we're going from right to left instead of left to right. Okay, that's 2, but make it the opposite. Okay, now G prime of 3. Well, I don't have information about G. I'm told that G is the integral from 4 to x. It's the accumulated area under f. But I'm told what f is. Well, equate G prime of 3 to something about f. G prime of 3 is the same as f of 3. F of 3 is the function value for 3, which is 2. What's G double prime 3? Well, it's the same as f prime of 3. F prime is the slope of the tangent to f at 3, which is what? 0. Okay. Now, what you will also be asked is, where does G have a relative max or min? Where does G have an inflection point? Okay? And now we go back to unit 4, but what it ends up being is just a step up. Okay? Because usually in unit 4, you'd be given the graph of f prime, and you're going to be asked information about f that you don't know. Well, now you're going to be given the graph of f, and you're going to be asked for information about g, which is the antiderivative of f. So you go just one step up. The problems end up being completed the same way as you did the unit 4 problems, but there's extra little questions that could be asked, because now you can actually find the exact values of this function that you didn't know, but you know the derivative of. Because we know that regular f is just going to be the accumulated area under f prime. That might not make sense to you right now, but if we do some examples, maybe it will. Okay? So here are 1, 2, 3, 4 problems. Let's do them. Question is, when does G have relative extrema? You know that that's when G prime, which equals f, changes sign. And then the second open-ended question here, where does the graph of G have an inflection point? You know G will have an inflection point when G double prime, which is equal to f prime changes sign. Okay, do these 4. Go. First question is G of 3 positive, negative, or 0. What is G prime of 3? When do we have relative extrema? When do we have inflection points? Check your answers with a neighbor. Right. Discuss, discuss, discuss. Help each other. You'll remember these types of problems.
Just use plug in 3 for which one?
We'll talk about how you just need to make the connection. And once you make the connection, you can then just talk about F, which is what pretty much you're talking about.
Do you know if it's maximum at zero? The extrema at all?
Oh, yeah.
Yeah.
Now, tell me if your extrema is a max or a min. Okay? You can tell me by looking at the graph of F whether the extrema on G that you found is a max or a min. All right, everybody, G of 3 is a positive, negative, or 0? Everybody, G of 3, positive, negative, or 0? Negative. It's negative. Why is it negative? It's the area from 0 to 3. You look at the graph, the area from 0 to 3, negative, beneath the x-axis. What is G prime of 3? 0. It's the same as F of 3. F of 3 is 0. Okay? Now, who can answer, raising their hand, where G has a relative extrema and if it's a max or a min? Or I'm just going to pick on something. All right, Ms. Boyce, I'm going to pick on you. Good. Excellent. X equals 3 and a min is correct. Now, if you were asked to justify or explain your reasoning for this, this is what you'd have to do. You'd say G has a relative extrema when G prime, and then you establish the connection between G prime and F. So when G prime, which equals F, changes sign, F changes sign from negative to positive at 3. Therefore, G has a relative min at positive 3. Remember, if your derivative is negative, your function is decreasing. Jet's going to the doctor. I'm worried about him. What about the inflection points, Mr. Head?
When F prime changes sign, so I thought it was where it changed concavity on F at 0 and 2.
The concavity changes, it looks like at 1, where we go from concave down to concave up on the graph of F. But when I look at values of F prime, do I look at concavity? What do I look at? Slopes. So it's when the slopes of F change sign. We go from positive slopes to negative slopes to positive slopes. We change sign at 0 and 2. You're correct, just your reasoning was off. Okay? So you'll say G has an inflection point when G double prime, which equals F prime, changes sign. And then you don't have to say the slopes of F equals F prime and the slopes of F change sign. You can just say F prime changes sign at 0 and 2. Or you say it occurs at 0 and 2. Okay? Let's do another one like that. I'm going to call on random people for their answers too. So be ready and make sure you know how to get the answers, or else you'll feel like, oh, I don't know. Go. That's the graph of f. I'm giving you that g is the integral from 2 to x. I ask you about g of 1, g prime of 2, g double prime of 2. I ask you, when is g increasing? And I ask you, when does g have points of inflection? This is 1, 2, 3, 4, 5, negative 1, negative 2, negative 3, negative 4. Okay, start discussing your answers after you get them, and then I will call on you randomly.
It's a sharp point, constant point inflection.
All you need is for f prime to change sign. Does it change sign at that sharp point? Good. That's the one tricky part, is people really get hung up on those. They think they're bad and they can't be answers, but typically they are. All right. Do we need another second? All right, another second of discussion, and then completely randomly I'll call up people. Completely random. I know. It's not completely random at all. All right. Miss Arella, G of 1 is a positive, negative, or 0? Positive is correct. Excellent. We're going from 2 to 1, which is the opposite of 1 to 2. We have negative area from 1 to 2, so this should end up being positive. Miss Quadri, what about G prime of 2? Negative 4. It's the same as f of 2, which is negative 4. And Mr. Rodriguez, G double prime of 2. 0 is correct. It's the same as f prime of 2. Miss Jagan, when is G increasing? There's an interval. 0 to 1 is correct. G is increasing when G prime, which equals f, is positive. F is positive between 0 and 1. And actually, we would include 0 because f of 0 is positive. We would not include 1 because f of 1 is 0, which means G prime of 1 is 0. And Mr. Koblesnik, what about, that was pretty good, right? When does G have points of inflection?
Is it on the slopes when they 0?
When the slopes change. That's important to know.
Change sign.
Change sign. Yep.
So x equals 2, x equals 4.
Almost. Everybody gets tripped up because they say, okay, the slope is 0 here at 2, the slope is 0 here at 4, so it's just going to be 2 and 4. But you just need the slopes to change sign. The slopes are negative until 2. The slopes are positive until 3. They are negative between 3 and 4, and then they are positive after 4. 3 is an answer. Just because it's a sharp point does not mean you exclude it and it can't be an answer. Because again, it's not necessarily when the second derivative is 0. Just like with a relative extrema, it's not necessarily when the first derivative is 0. It could be undefined, just has to change sign. In this situation, g double prime would be undefined, however, it does change sign. Okay. Actually, no, g double prime would be just, no, it would be undefined. But it changes sign at the point of inflection. Okay, well, that's great. Those are the exact same problems as the Unit 4 problems, except a step up, right? We're just starting instead of f prime, and these are f questions. I'm giving you f, and these are antiderivative of f, or g questions, okay? But it's the same thing. But now we have one extra thing that we can do, which is find absolute maxes and mins. We can find actual function values for the antiderivative of f. Okay? Now, again, I'm using big F just to switch up the notation on you. Typically, the questions will be G equals this, and you could just replace this big F with G if you're comfortable, more comfortable with G. Okay? The question is, what is the absolute max or min value of F, given information about regular F? Now, who can recall when we have max or min values on a closed interval? Right. It's called the extreme value theorem. Remember from optimization, the extreme value theorem. We have candidates for absolute maximum locations. Absolute max slash mins have to occur at relative maximum locations or the endpoints. If you have a closed interval. Okay? We'll have a closed interval. We'll talk about absolute max values of big F from 0 to 7. Okay? Well, first, we got to find our relative max or min locations. Where does big F, which you can think of as G, have a relative max or min, if this is the graph of F? Discuss that with your neighbors first. Okay, where do we have a relative max? 5. And I say relative max or min, really, because it doesn't matter. It'll just be a candidate. Remember, this is what we call the candidates test. Candidates test. So, relative max or min, we have one at x equals 5. Now, we know that this is going to be the location of a relative max because g prime, which equals f, goes from positive to negative. Okay? Now, all I can do now is actually compare function values like big F of 0, big F of 5, and big F of 7. These are my candidates. I will be able to get an absolute max and an absolute min from 2 of those 3, guaranteed. Every other point will be either below or will be in between the max and min value. Now, f of 0 would be the integral, and this is where we go back to this. We use this to find the actual values. Big F of 0 would be the integral from 4 to 0 under f, regular f. Now, this is 2 here, this is 3. Since it's 4 to 0, it would be the opposite, so this would be negative 5. F of 0, or sorry, f of 5 would be the integral from 4 to 5 under f. This would be 1. This is the integral from 4 to 5. It would be a positive area. Then f of 7, integral from 4 to 7, would end up being negative 1, because this is negative 2. Which means this would be the location of your absolute max, absolute min, and this is the absolute max. And if you were asked to sketch the graph of f, big F, not only do we do the sketching like we did in Unit 4, but we actually have points. It makes things a lot easier, because if we started kind of plotting down points, 0, negative 5, I can do that. 5, 1, I could do that. 7, negative 1, I could do that. And you'd be able to kind of start connecting those points to see you'd have a, max and a min, something like that. Of course, we should be using the signs to make sure the concavity is correct, make sure everything is correct. This is just a very rough sketch using some points. Okay, remember the first derivative, increasing, decreasing, second derivative, concavity. If I looked at the second derivative, g double prime, which equals f prime, we'd see it be positive until 2, 0 until 4, and then negative after 4. So that means I'd be concave up until 2. I would like flatten out from 2 to 4. And then I'd be concave down to my max and then moving into that min. Okay? So remember that from Unit 4, and when you do your homework, you'll have an example like that as well, where you're sketching, and remember how to sketch and go a little further by finding exact points that you can use. Okay? Now, with your calculator, I want you to do this problem. I'm giving you that g is equal to 3 to x of t squared minus 8t plus 7. And I ask you, what is the absolute max min of g on the interval from 0 to 10, closed interval? Now, so many students rush and put in their calculator the graph of this. And you could do this. You could actually go into your calculator and graph this function. Now, how can you do it? Well, the important thing is you can't use x's everywhere, or else that's not going to be the correct function. You'd have to be able to use multiple variables. I'll show you how you can do it. So we can go Math 9 to type in an integral, and we need to go from 3 to x. But I can't use x's. I have to use t's or a's or b's or something else. I'm going to use a instead. So alpha a squared minus 8a plus 7. And then I just have to make sure I go dA. Okay? And you're like, oh, I can find the absolute max and min. I'll just graph it and just like look at a table, or I'll just look at my graph. Well, watch what happens. What's happening? Nothing, right? Because you just typed in something super, super complex in your calculator. Will take a while to graph it. Now, this is actually an easier example. A lot of the examples that they give you on the AP test, it'll be so complex that it'll take your calculator 10 minutes to get through it. And then you don't even know how to like freeze it. And you're like, it's still working and I need to use my calculator on something else, but it's still frozen. What do I do? Well, if you end up in a situation where your calculator is still working, you press the on button to freeze it, and then you can get out of it, okay? So know that for the future. If you ever do something like that, get out of it by pressing on, or you can always take the batteries out of your calculator and put them back in, okay? But I don't want you to do that. I want you to think about this in terms of calculus, in terms of the extreme value theorem to find maxes and mins. You're looking for when G has a relative max and min. That's when G prime, which equals F, equals 0. Well, this is G. G prime would just be this with X's in it. When will that equal 0? Well, you could factor it. X minus 7, X minus 1 to get possible locations, 1 and 7. Well, now I can just find G of 0, G of 1, G of 7, and G of 8 and compare. 10, sorry. I went to 10. And it will take a lot less time for your calculator to be able to go from 0 to 0. You know, this is going to be 0. That's easy. But 0, oh, sorry, 3. We're going from 3. So this would be 3 to 0 of t squared minus 8t plus 7. Okay, it'll take your calculator a lot less time to be able to plug in this and calculate these definite integrals. Okay, so this is 6. I do it from the next one, from 3 to 1. Again, I can just go up and press enter, or I can go second entry, 3 to 1, 3 to 7, 9.3. I'll do 7. Negative 26. And then 10. You could also just look at the signs of your derivatives to figure out if these are going to be maxes and mins. Sometimes that would be quicker to just kind of eliminate some things. This is also 9.3. So we have 2 absolute maxes, and this would be an absolute min. Okay? You should be able to find the locations of the absolute maxes and mins for something like this that we've already done, as well as something like this if I give you a closed interval, okay? You just can look at the accumulated areas to do this. Now, before you leave, part of your homework is a worksheet. Part of your homework is a free response packet, some problems out of it. Please look at your calendar for exactly what you need to do. There is some book work as well. Hold on. Part packet, part worksheet, part book.